Hey everybody, and welcome to this video on some more properties of exponents. So let's get this show on the road. Alright, so now let's talk about what happens when you have a base and you raise it to an exponent, but then you raise all of that to another exponent. For instance, in the example m to the fourth and all of that to the second power. Well, we know what it means to square something. That means multiply whatever it is by itself 2 times. So in this case, it means multiply m to the fourth by itself 2 times. And we absolutely know what m to the fourth times m to the fourth is. That's m to the eighth. Now what would happen if we did something like m to the fourth to the third power? Same idea. We know what it means to raise something to the third power. It means take whatever it is, in this case m to the fourth, and multiply by itself 3 times. And we know what that's going to give us. That's going to give us m to the 12th power. And maybe you see a little pattern developing here. And maybe you can already anticipate what m to the 4th, all of that raised to the 4th would be, or m to the 4th, all of that raised to the 5th would be. Let's try another, this time with actual numbers. How about 3 to the 2nd power, all that raised to the 3rd? Again, we know what it means to raise something to the 3rd power. It means take whatever it is, in this case 3 to the 2nd, and multiply it by itself 3 times. And no surprise, we're going to end up with 3 to the 6th power. One more example. How about 3 squared all to the 5th power? Well, not surprisingly, we know what it means to raise something to the 5th power. That means take whatever it is, in this case 3 squared, and multiply by itself 5 times. And we end up with 3 to the 10th power. Now, we've started with all nice positive exponents, and it seems like every time we're simply multiplying the exponents. M to the 4th to the 2nd power, 2 times 4 is 8, we end up with m to the 8th power. Or 3 to the 2nd, all that to the 5th power, 2 times 5 is 10, we end up with 3 to the 10th power. Visually, this has been pretty easy to confirm, but now it's time to try a few with negative exponents and see if the property still holds. For example, in 2 to the negative 3rd power, all raised to the 2nd. Now in theory, if all we have to do is multiply the exponents, we should multiply negative 3 times 2, and we get negative 6, and in theory, we should end up with 2 to the negative 6th power. Let's see what happens. Well, we know what it means to raise something to the 2nd power. It means take the base, in this case 2 to the negative 3rd, and multiply it by itself twice. So we end up with 2 to the negative 3rd times 2 to the negative 3rd, and we know how to deal with this. When we're multiplying exponential expressions having the exact same base, all we do is add the exponents, and we end up with 2 to the negative 6th power, exactly what we thought we'd end up with by multiplying the exponents. Here's another. 4 to the 3rd, all of that to the negative 3rd power. Now this one's a little different. First we're raising 4 to a positive power, and then we're taking all of that and raising it to a negative power. In theory, if all we have to do is multiply the exponents, all we need to do is multiply 3 by negative 3, and that gives us negative 9. So in theory, our outcome should be 4 to the negative 9th. Well, let's see what happens. So first things first, we know what it means to raise something to a negative power. It means take this base, in this case 4 to the 3rd power, find its reciprocal, and the reciprocal of that is 1 over 4 to the 3rd power, and then raise that to the positive 3rd. And of course, we know what it means to raise something to the positive 3rd power. It means take the base, in this case 1 over 4 to the 3rd, and multiply it by itself 3 times. And eventually, we end up with 4 to the negative 9th power, which is exactly what we would have gotten if we had simply multiplied our exponents to begin with. 3 times negative 3 is negative 9, 4 to the negative 9th power was our outcome. One more example in which both exponents are negative. Here we've got 7 to the negative 2nd power, all of that raised to the negative 2nd power. So in theory, if all we have to do is multiply the exponents, negative 2 times negative 2 is 4, and we should end up with 7 to the 4th power. Let's see what happens. First things first, let's rewrite 7 to the negative 2nd power as 1 over 7 to the 2nd power. All right, now we've got something raised to the negative second power. And we know what that means. That means take the base, in this case 1 over 7 squared, find its reciprocal, which in this case will just be 7 squared over 1, or 7 squared, and raise that to the positive second power. And I'm sure you know what 7 squared to the second power is going to be. This just means take the base, in this case 7 squared, and multiply it by itself 2 times. And as we predicted, we ended up with 7 to the 4th power, which is what we would have gotten if we had just multiplied our two exponents. So it appears that our property holds no matter what the exponents are. So we see that if we ever have a base raised to a power, and then that whole expression is raised to another power, we simply multiply the exponents. Alright, now let's explore what happens if we have multiple terms within a set of parentheses and the whole set of parentheses is raised to a power. So for example, 2b to the 3rd power, all of that raised to the 3rd power. Well, our strategy is going to remain pretty similar. We know what it means to raise something to the 3rd power. That means take the whole base, in this case 2b to the 3rd power, and multiply it by itself 3 times. Alright, now we've got a long multiplication problem, and I think the easiest way to simplify this is to focus in on the individual bases. So for instance, I see 2 times 2 times 2 for a grand total of 2 to the 3rd power. We also have b to the 3rd times b to the 3rd times b to the 3rd for a grand total of b to the 9th power. And if we compare our product to our original problem, it's kind of like that exponent of 3 applied to both the 2 and the b to the 3rd individually. Let's try another. How about x to the 3rd times y to the negative 4th, all of that squared? Again, we know what it means to raise something to the 2nd power. It means take the base, whatever it is, and multiply it by itself 2 times. And in this case, we end up with x to the 6th times y to the negative 8th, which, if we want to write as a fraction, is x to the 6th over y to the 8th. And it's kind of like looking at the original problem, like we took that exponent of 2 and applied it to the x to the 3rd power and applied it to y to the negative 4th power. And note that there's another way we could have handled this problem, and this is the way I actually prefer to do it. And this way starts with, take your original problem and before you do anything, try to rewrite it with all positive exponents. Which leaves us x to the 3rd over y to the 4th, all of that squared. Again, we know what it means to square something. It means take whatever it is and multiply by itself 2 times. And of course, we ended up with the exact same answer that we did before. Again, it's kind of like this exponent of 2 applied to both the x to the 3rd and the y to the 4th. So, as of now, it appears that if we are multiplying or dividing our different terms within a set of parentheses, and then raising that whole quantity to some power, each of the individual exponents is multiplied by the outermost exponent. Let's do one more example just to make sure. Alright, this example is way harder than the two we've already done. And I see that we have negative exponents inside of the parentheses, and we've got negative exponents outside of the parentheses. So what I'm going to strongly suggest before you do any real evaluation is this. Try to do whatever you can to rewrite this problem using all positive exponents. So first, let's rewrite the inside of the parentheses, rewriting that h to the negative 3rd as a fraction involving positive exponents. Even though we've taken all the exponents inside of the parentheses and made them positive, we still have a negative exponent outside of the parentheses. But we know what it means to raise something to the negative 3rd power. That means take this base, in this case m squared over h to the 3rd, find its reciprocal, in this case h to the 3rd over m squared, and raise that to the positive 3rd power. And we know what it means to raise something to the third power. It means take that base, in this case, h to the third over m squared, and multiply it by itself 3 times. And we end up with h to the ninth power over m to the sixth power. It's kind of like that 3 as an exponent applied to both the h to the third and the m squared. And note to self, from this step, you actually could have done the same thing. You could have applied this exponent of negative 3 to both the m squared and the h to the third. And we see that we end up with the exact same result. And in fact, from the very beginning, you could have applied this negative third power to both the h to the negative third and the m to the second. And again, you obtain the exact same result. So in general, if we ever have multiple terms in a set of parentheses, whether we're multiplying them or dividing them, if we raise that whole set of parentheses to a power, we simply multiply that power by each of the individual exponents within the set of parentheses. And one big note, these properties that we just talked about do not hold when there's addition or subtraction in the parentheses. If there's addition or subtraction, that's something we're going to deal with later, but as of now, we don't have any way to simplify these. All right, time for some practice problems. But before we dive in, here are some suggestions that I have for how I like to simplify these difficult exponential expressions. First things first, I want to simplify everything inside of the parentheses. And to do that, first, I write everything with positive exponents, and then I take care of any simplifying. And then I deal with everything outside of the parentheses. And to do that, I first make sure that whatever that outside exponent is positive. And once that's the case, then I apply that positive outside exponent to all of the individual exponents within the set of parentheses. So why don't you pause the video and give this one a try, and when you're done, I'll walk you through how I would do it. All right, first things first, I took what's inside of the parentheses and I saw we had an n to the negative fifth, so I rewrote what was inside of the parentheses having all positive exponents. Then I saw that we had a negative 3 as our outermost exponent. So instead of having a negative outer exponent, I changed that to a positive outer exponent, but of course changed what was inside of the parentheses to its reciprocal. Then I knew it was time to apply that exponent of 3 to all the individual terms within the parentheses. Now note, I wouldn't actually suggest writing these arrows. I just did them to visually show you exactly what was going on. And then we ended up with n to the 15th over 3 to the third times n to the 12th. All right, let's try another. All right, why don't you pause the video and give this one a try. All right, one more example. All right, why don't you pause the video and give this one a try. All right, guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.